Welcome to this video. Today we're talking about parallel scaling law for language model. This paper was published 6 days ago by the Current team and the Alibaba group. And the idea is that the authors are introducing a new paradigm called parallel scaling, okay? And we already do have two paradigms called parameter scaling and inference time scaling. And parameter scaling just regards to the idea of just making the model bigger and then getting better performance. And the inference time scaling refers to the idea of DeepSeek. They introduced it with the reasoning model. And there you just increase the reasoning tokens by using a reinforcement learning paradigm to train it, okay? And now the authors are introducing here called a new scaling law called parallel scaling, and the model use parallel computation. So the overall idea is that the model we are not increasing the parameter size of the model, but we're using the model more times on the same input, but not on the complete same input. We do we do a learnable transformation before it, and then we feed this into our model, and then we got more output. So if we have p learnable transformations, we get p outputs, and we aggregate them with a learnable MLP layer, okay? And the overall idea is now that if we're doing this, the model, we are not increasing the parameter size, but the model has more computational power, and can see on the on a similar input with different views can have different views on the same input, okay? So I can look from this perspective and from the other perspective. This is the intuitive idea. And what they find out is very interesting, I would say. With p-parallel streams, it's similar to scaling the parameter by log p. So what does it mean? If we increase p, if we choose p 1024, for example, this is similar to making the model 10 times larger, but is more efficient to maybe just increase p, because if we increase p, our memory is not going up so much compared to increasing our parameter size. Okay, so that's pretty cool. Let's just have a small look to understand the three paradigms better. So we have on the top left our parameter scaling, where we just making the model higher, and this brings a high space cost, because we have to save the model into our GPU memory, and if we make the model bigger, we need more GPU memory. Then we have inference time scaling, where we have reasoning tokens, and each reasoning token helps the model to think about making the prediction of the next token. So this takes time in inference, but also training, and and now we see the idea of parallel scaling, and here we see we have an input, and we are adding p learnable transformations. So we have, for example, in this picture, 3 learnable transformations, and those learnable transformations are just tokens we add as a prefix, okay? So each sequence gets we are duplicating each sequence p times, and then adding p different tokens onto at the beginning of this sequence. For example, here we have we can see it here. The red refers to our prefix that we add to our normal sequence, and one interesting thing is they're not just using one token they're adding. They showed it in abstract. They're using up to 96 tokens for just one learnable transformation. Okay, so if we have a long sentence or sequence, then we put 96 parallel 96 tokens. We are appending 96 tokens to this sequence in order to get a learnable transformation. Then we are just putting those inputs through the model, and we get then P outputs, and at the end we are aggregating those P outputs with learnable aggregation. Specifically, they are using a MLP. So they are concatenating all those outputs, then put this into an MLP, and using a softmax in order to predict the weights of how we combine this. So if we have output 1, output 2, and output 3, we just learn W1, W2, and W3, and we add them all together, okay? And so the model predicts W1, W2, W3 in a fashion, and they use for this like just a softmax at the end of the MLP block, and it's a very small MLP block, okay? And let's have a look on the results. And yeah, the scaling results can be seen in this picture. What can we see? We have on the x-axis the parameters. As always for scaling laws, we are looking at in a logarithm way, so the x-axis is logarithmic, and on the y-axis we can see the loss. Okay, and the different colors referring to the different numbers of parallel streams, so how many learnable transformation we have, and how much parallel computation we are using. Okay, so the base case with P equal to 1, so normal training, we get a loss here, so 1.0.3, and if we're now increasing it to 8, so we are using 8 learnable parameters, we can see that we are achieving the same with much less parameters, so actually with 45% less parameters compared to just a normal way we normally do it with P equal to 1. Okay, so that's pretty interesting. We can scale our model just by using by increasing the parallel computational capacity. And one more, I think an even more interesting thing is here that the GPU memory obviously is going down. So on the x-axis we see the GPU memory, and on the y the loss, and we can see, okay, with P equal to 8 we achieve with a similar GPU memory a much better loss. Okay, and we see this for all those models. Okay, so they trained here 3 models, or printing 3 models with 1.6 billion parameters, 2.8 and 4.4. Okay, and also the latency goes down. So I would say it's pretty interesting what they found out. Let's just have a quick view into the introduction. Here they're referring just to the idea, okay, inference scaling brings some problems with it, and one problem is that we are maybe generating up to 900 reasoning tokens for a very easy task like calculating 2 plus 3. This is why they asked their universal and efficient scaling approach that avoids excessive space and time costs. And they found the idea of parallel scaling by looking at the classifier-free guidance of diffusion models, where you also use parallel computation. So let's have a look at the classifier-free guidance, and we switch to diffusion models, and there we have 2 outputs. So our idea is the diffusion model, we want to generate an image conditioned on a text, and we can just do it without the condition in the first way, and then do a second computation where we use the condition, so the text also as the input to the model. So we get 2 outputs, all the parameters are the same, but we are changing our input in a little way. So by using one with condition and one without condition, and here we are subtracting the difference between condition and unconditioned. So this says us how different is a condition with unconditioned. If we now add the this difference to the unconditioned, we get more into the way of the condition. And this worked pretty well in the diffusion models, and also now used in in the NLP community. The authors find this quite surprising why this works, and they say, okay, it lies in the double computation because the model has two looks on the same input, so one on the here and one here, so we also have two computations. So this is why they propose the following hypothesis: scaling parallel computation and hence the model capability with similar effects as scaling parameters. Okay, so it's we can use parallel computation to get a better model. I would say we can just have a small look on this table. What we can see here, different scaling paradigms. So we have dense scaling, which just refers to making the model larger. We have a mixture of expert scaling, and we have inference time scaling and parallel scaling. And what we can see is that the parallel scaling has moderate inference time, moderate inference space, so how much GPU memory it takes. If we compare this to the dense scaling and mixture of expert scaling, okay, they take a lot of memory because we are scaling, we have more parameters, we have to store more parameters on the GPU. So this just is a small overview of the different paradigms and the benefits of it. Okay, the last important point here is that that they found that reasoning-intensive tasks benefit more from path scale, which suggests that scaling computation can effectively push the boundary of reasoning. So that's pretty important. Currently, we want to get better reasoning, and they found out, okay, path scale also has a great benefit for reasoning tasks, so coding or math. And then they're saying that the training cost can be significantly elevated through a two-stage training strategy. So this means you can just do it directly from scratch by training, or you do a two-stage pre-training where you split your pre-training data sets into two parts and use the first with the normal pre-training, and then just do for the last 10% of your pre-training data sets at the other path scale scaling, and this also achieves pretty good results. So you don't have to do it on your complete pre-training data sets. And so let's just have a look at the math. Here they are introducing the classifier-free guidance from the diffusion models, and they're making it a little bit more general here. So we have our outputs g of x, and this output is aggregated based on two inputs of our model, or two outputs of the model. F theta of x and f theta x hat, and f theta x hat is different than x. So for x hat we for example added our prefix, and here we are not adding a prefix, so we have two different inputs into our model. Then we are using the same update rule as I showed above here. Okay, and what they find out is that that f of x is unable to learn the capability of g of x during training, because we could argue, okay, they both are using the same parameter, and why cannot just f of x should be able to get the same output at the g von x, because this is just a linear interpolation, and f of x should be able to get the output g of x, but they found out that this is not possible and not achievable. They argue this with that the fundamental reason lies in g of x having tried the computation as f of x. Okay, because I can have two different looks at my input, I can get better results because I have twice the computation as f of x, and this inspires us to further expand the equation into the following form. Okay, here we just have p is equal to 2, and here p can now be larger than 2. We can use it as a hyperparameter, and what we can see, we're just using an average here, or dynamic average. And because they're using softmax to generate the W's, this sums up to 1. Now we have our p different inputs into our model, and we get p different outputs, and all those outputs we are aggregating. One interesting part maybe is that we are doing it, as I understood it, if I understood it in the right way, we are doing it on the logits, so not on the latent space, but directly on the logits, okay? And yeah, and then we're combining these. So the only parameter that they have to add is a prefix token they're adding to the sequence, and they use the MLP. They're saying it here for output aggregation. We employ a dynamic weighted average approach utilizing an MLP to convert outputs from multiple streams into aggregation weights. Okay, this increase about 0.2% additional parameter for each stream, so it's not so big. I just jump into the appendix to understand the output aggregation better. So we can see we have an MLP called H, and first of all we're concatenating all the outputs of the model, and then we put the model, so the concatenated output, which is a long tensor, we're putting it into our MLP. The MLP is very small, and then we predict the weights by using a softmax, and yeah, then we use weights to aggregate the output weighted by those weights. Okay, and what they find out is that in the early stages of training, the model may assign nearly all weights to a few streams, leaving others with near zero weights. To avoid this phenomenon, they're adding a hyperparameter called epsilon, and this epsilon is a constant that we are adding to our weights, so that each output is at least used by a constant which we can use as a hyperparameter, so that we are using every stream at least a little. Let's also understand the input transformation completely. And the problem is, if we choose a high p-value, this means that we need p different inputs to our model. And the question is how we generate the p different inputs. In the image domain or vision domain, we can just make some transformations on the image, for example masking or putting a filter or Gaussian noise onto those images. In the language domain, we can use a different transformation, and they use a transformation that apply to the input embedding. Okay, what does it mean? For example, if we are using soft prompting, this means that we change our input in a way that we are adding to the sequence a number of prefix tokens. So we have our sequence, and then we add our prefix tokens, and then this prefix tokens are managed the same way as all the other sequence tokens that represent actually tokens, because those prefix tokens are not representing any really tokens that we can translate into language. They are using a different technique, and I think it's maybe a little bit confusing by the figure we looked at the beginning, because they used a visualization like this. But the authors are saying here we utilize prefix tuning to implement input transformations. To be specific, we first duplicate the input x into p parallel copies, distinguish them with different prefixes in each attention layer. But then the prefix is not managed in the same way as a sequence token, okay? Because we are only adding the prefix into the specific attention layer. Okay, so in each attention layer we are adding the prefix, but then we remove it, or we don't have to remove it, because we are only using the key and value. So maybe let's visualize this to understand this. I just draw the attention matrix in order to understand the prefix tuning a little bit better. And the big difference between prefix and soft prompting is, by soft prompting we have our token, our prefix token behaves like a real token, but here our tokens we are just using the prefix token in the attention matrix. So we added one more key here, and this is our prefix key, and then we calculating the dot product between key 1 and this key, and we get our attention value. And what we can see is that this prefix has an impact on our first tokens in the sequence. We can see the impact here, so it depends on the dot product of it, normal attention. And the difference is that we are not having a fourth token, so we are not having a token for the prefix itself, but in the next attention layer we are adding again here the new key and also then the value of the prefix tokens. Okay, so that's a difference between prefix and soft prompting, and and they use prefix tuning. Let's now jump into the theoretical analysis of the scaling law. So in part 3.1 they're referring to the chinchilla scaling laws and say for each stream that the each stream has scaling laws like this. So we have an entropy, this is our irreducible error of the natural text, and we have a constant a, e, and alpha, and then we have a parameter n, and this n refers to our model parameters. So if we increase n, our error goes down, okay, in a power law spectrum. Of the chinchilla scaling law, they introduce their new scaling law, parallel scaling law, and what we can see here, we also have our parameter n, and we have two more parameters. One is the diversity, and the diversity calculates how diverse is the output of the p streams. So if we have p streams, we look at the output, and if they're correlating a lot, this means that the outputs are not diverse, and therefore the diversity is smaller, and this makes the loss higher. What we could also see is that p refers to our numbers of parallel computations, and when p is 1, so the correlation of the diversity, so this p is not referring to the this p but to the p in this equation here. And they're saying, okay, if we say p is equal to 1, then the diversity is, there's no diversity, and therefore the this parallel scaling law is the same as the normal chinchilla scaling law. But if we are using a different, or if p is unequal to 1, so we have a correlation, then we have a benefit by using more parallel computations. So from this, they are introducing the practical parallel scaling laws. So they try to train a model and have a look how the loss is really scaling on a real example. Therefore, they trained a transformer, and what they could find out is that the scaling laws look like this, where k reflects to our numbers of parallel computations. So k is our was our p, and p is now our k. And we see that we have the diversity is now given by log of p plus 1, okay? And they found that here based on the finding of a logarithmic trend in because they found a logarithmic trend in their training loss, they used the logarithm. And one very interesting fact they found out is that they looked at the key value for two different data sets. Okay, so they trained two models. One is named Stack V2, and this is more coding and more reasoning. And then we have a Pile dataset, and Pile dataset is more about memorization. Okay, and you achieve a good loss if you can do good memorization, and on the Pile and for Stack you have to understand more math, more coding, some more reasoning. And what they could find out that the k value of Stack V2 is larger than for the Pile dataset, and key reflects to our parallel computations, and therefore they're saying now model parameters mainly impact the memorization skills, while computation mainly impacts the reasoning task. Okay, for memorization it's better to increase n because we don't have the same benefit for increasing k, because we have a value of 0.33 instead of 0.39. And this is why they're saying that if we have a reasoning task, this techniques, parallel computation helps more, and for reasoning start instead of memorization tasks. Okay. And if we now look at the table 2, we can see that we can see the different p's, and in regard to the different model sizes, and what we can see is, okay, on the downstream task the model gets a better performance if we choose a higher p for all the different model sizes. So yeah, we can see that the scaling laws can work there. So I would say pretty interesting results here. I really like the results here, and one more cool thing is that the parameter scaling, or actually the parallel scaling, use 20 times less the memory than the parameter scaling for the same loss. Okay, so if we look here, we can achieve a 1.0.4 loss with 20 times less memory, because the blue lines corresponding to the parameter scaling and the gray to the parallel scaling. In part 4.1, they are saying that two-stage pre-training can work. So what is a two-stage pre-training? Yeah, we are just using normal pre-training on the most of the data set. So we use 1 trillion tokens for doing normal pre-training, so p is equal to 1. And then we can see we can then even scale it with increasing the value of p. And we can see a great decrease in the loss in the stage 2. I hope that you enjoyed this video. I will put the link to this paper into the video description. Please press the like button if you like this video.